Right. Second. So good afternoon all. Right. So we have been doing circuit labs for almost now one semester, right? So at least AEC and DEC. So now most of you have done the experiments, and specifically in DSD lab, okay, where we had to work on the kits. Okay. If I don't get the desired output, what is our normal procedure? Yeah, ideally that should be, but what we normally do, remove everything and rewire, right? So that is what we normally tend to do. Okay. So instead of debugging the circuit, we always reconnect the circuit. So we don't go to ascertain why I am having a issue. Okay. So that is because most of us don't want to spend time in debugging, because we assume that it is a very trivial thing to do. Okay. And it is a time consuming thing, so we don't want to waste our time. Okay. So these two are the major reasons cited why we don't debug. Okay. So instead of that, rebuilding a circuit becomes much simpler process. Okay. But this is okay in a lab setup. Okay. In a lab setup this is okay, but if you are trying to come up with a product of your own, okay, we cannot avoid debugging the circuit. Okay. So this is a must. The product can be a software product, a hardware product, or an embedded product where we have both software and hardware. Okay. Unless we debug the circuit, you are not going to have a product which is sort of foolproof, okay, which works as per the specification given. Okay. So this is what it is. Okay. So most of the time we tend to concentrate on designing the circuit, building the circuit, but we don't tend to concentrate on testing the circuit. Okay. So if you look at the life cycle of any product development, okay, in the student life, the way we plan the product design or project work is maybe around 50% of the time or 30% of the time in design. Okay. Then say around 40% of the time for getting the components and building the circuit and connecting them, and rest of the time for preparation of the report. We hardly account for any testing. We assume that whatever we build will work first time we connect. That is the assumption. Okay. It is not only when we come into engineering, maybe in the third semester, no, final year also you will be doing the same thing. Okay. Because we assume that whatever we do is going to give us the valid result. Okay. It is like we are confident on ourselves. Okay. But there is a fine line between confidence and overconfidence. So we generally, when we are used to designing, we tend to go towards the overconfidence case, assuming everything will work. And the problem happens on the day when we have to present the result. Generally circuits don't work. Okay. The day when you have to present your work, they don't work. Till yesterday it was working, today it is not working. That is a common excuse we find most of our students giving. Don't worry, when we were students also, we also have done that. Okay. So it is nothing to be ashamed of. Okay. Only thing is, now we want you guys to be better than us, so we are trying to bring this series where we tend to make you more accustomed to design. Okay. Whereas when you go out and you join a company, in case you join a hardware design or embedded design company, maximum time is kept for testing. Okay. Or if not maximum, at least 50% of the project time is meant for testing alone. Okay. It is meant for testing alone, and 50% of the time design integration, if you have multiple teams which are working to integrate all the results and come up with the product. So that is how the plan is. That is minimum. Okay. They would want to have more and more testing time. Okay. So this is what is expected. Now why is this testing very important? Why do you think we have to test our designs? So what could be the reasons? Take a simple example. You are assume that you know how to prepare coffee. Okay. You have been practicing how to prepare coffee. Okay. Now suddenly some 10 or 15 guests come to your home. Okay. And your parents are speaking to them, so preparation of coffee falls on your head. Okay. So you are supposed to now prepare good coffee, and your parents are telling, generally when guests come, my son or daughter prepares the best coffee you can have. That is how they speak. They are good at it, right? Nice. So you are now all pumped up. I will prepare coffee. You prepare, okay, and you go and serve it. Now, as soon as they drink, you have forgotten to put sugar, okay, right? Now you are used to preparing coffee, but that day, because it is like a high pressure now, the guests are there, you have to do live example, you forget. Now what is the impression? The specification says what coffee comes out is the best coffee, and what they have may be best for some case, okay, who don't want sugar in their coffee, but for general case it is a not so good coffee, right? Why is that? You have not tested or tasted your coffee before serving. So as trivial task as preparing coffee, you want to be tested and then served, okay, to ensure the quality is maintained. So the same goes for any of our job, any of our product development, or rather any of our tasks. So we always have to cross check whether whatever we have done is up to the mark or not. Okay, so testing is very important. Now coming to electronics, okay, coming to electronics side, whenever we design a product, okay, if we, the first thing what we need to do is we have to see whether the functionality is fine. What I want is what I get. That is the expectation. Customer says, I want the light to turn on when I press the switch. Light should turn on. Okay, light should turn on. That is the minimum expectation. So there is something known as a functionality test, where we test the function of the circuit. Okay, this is one thing. Okay, then there is something known as a prototype test. Okay, so functionality test can be done via simulation. So I come up with a simulation. Okay, I know that this works in this fashion. Okay, and then I build that circuit on a breadboard and see whether it works. It works fine. Okay, then I do a PCB routing layout and I send my product to for fabrication. So once it gets fabricated, the board comes to me. Okay, what I have now is a prototype of the board. Okay, so this is basically a similar version of how the final product is going to be. So I have to test that. So that is known as prototype testing. Okay, so prototype testing is actually the test which is performed on the first version of your product. Okay, first version of your product. So you have to do testing on that, find out if there are any issues. Okay, there can be a lot of issues. Okay, so as we test, we will find out those issues and we will try to correct it. And if there are serious issues, you may have to rerun the board. Okay, get it again fabricated again, so that you have a fault free board. So this is what we are going to have. Then finally, once everything is okay, you find that everything is working as expected, then you are ready to ship the products. Okay, then the bare minimum testing which is required to ensure that board works or not is basically on the manufacturer of the board, and that is known as manufacturing testing. Okay, so what you build is something like a built-in OS or BIST system, not built-in OS, sorry, BIST, built-in self-test. So you design a module which will test your boards, okay, automatically test your boards. So the manufacturer, he doesn't know what is there, he will just run this test algorithm to check all the board is working fine or not. Once it is fine, he will put a sticker QA passed. This you would have seen in most of your consumer equipments, QA passed they put. Basically this is what is done. There is a bare minimum test what he runs, and if it works fine, he will put that seal QA passed, and then it can be shipped. Okay, so this is what happens in PCB or hardware manufacturing, or this process is valid even for embedded design as well. Okay, we clearly differentiate between the hardware testing and software testing. The reason for that is the teams are basically different. Okay, but when we are doing a functional test, both the teams have to be present there. Okay, because both hardware and software should work in unison for the output to come. Okay, so this is required. So whenever you are testing, you will always be testing with the software engineer if you are the hardware engineer, or if you are the software engineer, you would be working with a hardware engineer. Okay, so bare minimum knowledge on what is happening in software and what is happening in hardware is necessary for any embedded engineer. Okay, so this is what is required. Okay, so now coming to, okay, so we know that we have to deliver a good product, and for that testing is necessary. Now depending on where we test or where we find a fault, okay. So if I find the fault, for example, we'll go back to the coffee example. If you had found out that whatever coffee you prepared didn't have sugar, okay, if you had tested it before serving, okay, you could have saved a lot, isn't it? Your reputation would have been saved. Now after giving there, the person who is drinking, he says there is no sugar, then you test it, it is no use. You are ascertaining there is no sugar, but your reputation is lost. So the later stage of your product you find a mistake or a fault, more costly it is. Okay, this cost can be in terms of reputation, money, okay, or the time required to recover from that fault. Okay, so this is what is there. Now to really understand this, take an example of a IC. You have all used the IC in the, digital lab, right? So basically take the example of a NAND gate, right? So that NAND gate has 4 NAND gates in a single IC, right? You build your circuit assuming that all 4 of them are working fine, and you build a complex circuit, have hundreds of wire coming from that suitcase, coming out, going here, there, everywhere. Okay, there is now no space. Okay, there is no space where you can just put your hand and remove the IC. That is the situation, you assume. And then when you are now giving the inputs, you don't get the outputs as expected. Now you see what could be the problem, and you find that one of the NAND gates inside an IC was not working. Okay, was not working. Now to correct this fault, what all things you have to do? Remove all the wires, okay, then remove the IC, replace it with a new IC. Okay, look at the time spent. You have to remove all the wires, and maybe that may be hundreds of wires which is there, so you have to now reconnect all those wires. Assume this happens in the exam. We have 3 hours where we have to finish all this work, right? So you need more time, you will panic, okay, because you have to finish. You have a dead or a delivery time where within which you have to deliver your output. So now more chances that you may not recover from that. Okay, as simple as that. Same thing happens for any product. If I don't release my product at an appropriate time in the market, I will not make money. It is as simple as that. Okay, so that is why they want to find faults as early as possible. Okay, this is more so now if it is happening inside an IC, because if inside an IC if there is a fault, once I fabricate it, if it is not working, I have to simply throw away that IC. Assume such a fault exists in one of your processors, Pentium processor you buy, assume that had a fault. That cannot be used on a desktop, you have to simply throw away, and it is around 5,000 to 6,000 rupees for a processor minimum. Okay, it will be much more than that, but minimum. Okay, you can't recover, you have to simply throw away, and that entire batch whichever has a fault, if I manufacture thousands of that, I have to simply throw away all 1,000 of that. Okay, so you want to find the fault as early as possible. So if you see this curve, what it says is what is the increase in cost of finding a bug. Bug is basically a fault. Okay, bug is a terminology normally used in software. We consider it as a fault, but here and there we just tend to make use of the same terminologies, so it shouldn't be a problem. So bug or a fault, so the cost required to find this is basically increases exponentially as late as you find. Okay, so earlier you find, you can always come out with a solution and improve your design. Okay, so this is what is there. So one of the best practices what we need to ensure that we follow is test each and every stage. Stage by stage you have to perform the test. If I am using 2 AND gates, first AND gate you test, connect the inputs, check the output, it is working fine, make the next connection, check that part, then add these 2, interface these 2, and finally you are bound to get proper results in that. So every stage you need to test as much as possible. Okay, when I say test, we have to see what test case I need to give. Okay, what is the testing or value what I need to consider, what inputs I have to give to minimize my testing time, as well as to improve the quality of the output. So these things come in hand. Okay, or we have to keep remembering about these things. Okay, so basically this gives the increase in cost as like compared to the life cycle of your product design. Okay, so this is what we have. So So now coming to this, I have already told hardware testing. Now we will come to the hardware testing concept. So hardware testing basically is a multi-purpose function, I would say, multi-purpose function whose main purpose is to detect faults, and these faults can happen in different life cycle areas. That is, it can be in fabrication, or it can be in the design, or it can be failures due to operation. Okay, when you are operating the circuit, because of the stressful conditions what you make the circuit to work at, and it can lead to a fault. Okay, basically what we are trying to find is issues which can cause poor reliability. Okay, that is the main thing of hardware testing. Okay, similarly software testing also, I can just replace that hardware with software. Okay, there also it can, there instead of fabrication it would be the design is same, failures due to stressful operating conditions also is true there. Okay, instead of fabrication it would be coding. Okay, you can have a coding fault. Okay, you have done the flow diagram properly, but when you code you have made a mistake there. Okay, so that can lead to failure in your circuit operation. Okay, now these functional tests, prototype test and manufacturing tests I have put here, basically dealing with the hardware part. Okay, dealing with the hardware part. Okay, so now little bit of terminology which we should remember when we are performing any testing. The first one is the defect. Okay, we say that a electronic system is having a defect when there is a difference in the behavior compared to the design. Okay, difference in the behavior compared to the design. Okay, so then we call it as a defect. Okay, it may be design, I am expecting a 1k resistor there. Okay, but when I fabricate the device and it comes back, I have a 10k resistor there. That is also a defect. It may not cause a large fault or a large failure, but it is still a defect. Defect is anything apart from your intended design. Okay, so this is what it is. Okay, button, I expect the button to be like this. If the button is sewed on the opposite side, that is a defect. Button is sewed slightly down, that is a defect. I may still be able to button my shirt, but problem is the look will go bad because this will come like this. Okay, so that is a defect. Okay, now fault basically is a representation of the defect. Okay, representation. So because of that defect, what happens in the operation of the circuit, so that is the fault. Okay, so defect and fault go hand in hand. Defect is the cause and fault is its representation. What happens, how you find out there is a defect. Okay, so this is, I have a series resistor of 1k, not connecting that resistor is a defect. And what is the fault? Because I don't connect, I am not getting any voltage. That is the fault. Okay, is this clear? So assume that I have a series resistor, not having that resistor is a fault, is a defect. Not getting voltage because of absence of the resistor is a fault or a failure. Okay, so this is what we have. And error basically is a serious failure which causes a complete what we can say, it's like I expect my circuit to give a high, it gives a low for the same set of inputs, then we say that it is an error. Okay, serious faults are considered to be errors. Okay, so this is what we have. Now normally we use two words, one is debugging, the other one is troubleshooting. Although they are used interchangeably, they are slightly different. Okay, so debugging usually means why the circuit is not working as planned. Okay, why it doesn't work as intended. Okay, whereas troubleshooting is, I know that the circuit or design is fine, it is working fine, but that particular copy of that design is not working fine. Okay, so it is like I have two phones, same make phones, one of them is working, one of them is not working. Okay, so now if I try to find out why the single phone is not working whereas the other one is working, that is known as troubleshooting. Okay, troubleshooting. So you are working on a single problem where most of the circuits work, some of them don't work. So this is the slight difference between these two. Okay, so this is what we have. Right. So now the first exercise what you are going to do in the sense as a designer is you have designed your circuits, okay, you have designed your circuit and you have sent it, made the layout and you have sent it to the fabrication house to make the PC board. Okay, so this is a PC board, okay, where they give the space for the components, okay, they give the space for the components and internally they will have wiring, okay, everything is there within this board. Okay, so this is the first thing what you get as a hardware engineer. Okay, now after this what you are going to do is you are going to mount the components on this to complete the assembly of the board. Okay, so there are some steps you have to take in order to ensure that the board works as intended. The first thing is you are going to test this bare PCB. Okay, so there are some minimum tests what you need to run on a bare PCB. So you have designed this, you know it is supposed to work in a particular fashion, you know how each and every pin is connected. Okay, so what you need to do is inspect the board. Okay, first thing is always first step we inspect the board. So if you see here on this board there is some numbers written, some IC numbers written and some component values are also written, reference designators are written. Okay, so these are written so that when we place the components we know which component we are going to place at which place. Okay, so this is known as a sill screen. Okay, the front top where you can see white colored ink. Okay, if you are not seeing, let me pass the board later, you can see that. So this is known as a sill screen. So this gives what component goes where and such information are put on the sill screen. Now for small boards or low component count boards you will have the sill screen. If you have large number of components or very small board they will not have a sill screen. Okay, so that is there. Okay, for example if you have seen a Arduino board they will not have complete sill screen, only some components they will give the sill screen because the board size itself is small. Okay, so they can't fit all the part numbers, reference designators and so on and so forth. Okay, but it is generally a good idea to have a sill screen. Okay, so first one, look at the board, okay, and see if there are no errors or no mistakes on this. Okay, one common mistake can happen is, see here, now wherever I have the component being placed, this is a through hole board. Okay, you have a pad here where you are going to solder the component. Okay, you are going to solder the component. One common mistake what can happen is the sill screen what you have given sits on top of the component pad. Okay, and what is the problem with that? That sill screen is a insulating material. Okay, now you try to solder there, your component cannot get soldered to the board. Okay, so this is a problem. Okay, so that is why even the bare board has to be inspected to see there are no problems. Okay, so this is what is required. Okay, another one what we do is with the ohm meter we measure the impedance between the traces. So whichever points I have a connection, that should show me low voltage, low resistance path, and whichever part they are insulated they should show a high impedance value. Okay, when you measure using your ohm meter, that is multimeter in resistance mode. Okay, so that is what you need to get. Okay, if everything works fine, then we can go and start assembling the board. Now it can so happen when this is fabricated, okay, two pads, closely lying pads, internally they can have a short. Okay, so that and all can be found out in the bare PCB mode itself. Now why is it necessary that? Assume that two closely lying pins were, one was say VCC, another was some IO pin, okay, to which you are not supposed to give a high current. Consider this case. You didn't check this, you simply put your component inside. Now because there was a short, as soon as you power on, that IO pin goes for a toss. So once that IO pin goes, basically that IC is useless now. Okay, that IC becomes useless. So now cost of not detecting the fault, one IC lost. Okay, so all these things have to be done in the bare PCB itself. Now once you ascertain that this is working fine, then what we do is we assemble the board. Okay, when we assemble the board, what we do, we mount the components in its appropriate place, solder it. Okay, now if it is a small board we can do soldering ourselves. It is if you are working in a company where they make huge boards like your motherboard inside your desktop, they will not solder it themselves, there is a separate automated soldering process which it will go through, and you get the assembled board. Now once we get the assembled board, again the first check is a visual inspection, where you see that whether the components are placed properly or not. Now this is an example of a assembled board. Okay, this is an example of a assembled board. So you see I have assembled a LCD here, and I have put a microcontroller IC over a base, okay, IC base, and there are some IC bases here, and there is an LED, there are some switches, there are some connector pins, more LEDs, and so on and so forth, different capacitors and so on. Okay, so the first thing, I do a visual inspection of this. Now visual inspection, why is it necessary is, a component can be mounted wrongly. For example, here this capacitor, it is a polarized capacitor. Okay, so that has a positive and a negative. Okay, if you connect that in reverse, it is actually dangerous. There is a chance that that capacitor can blow. Okay, that is a chance. So we have to be careful about it. So by visually looking at whether it is connected properly or not, I can find out such errors are there or not. Okay, another one here. Now here I have put this component on a IC base. Assume that you have mounted or soldered this IC directly onto the board. That is also possible. Now you have to check whether the pin number 1 of this IC is aligned to the proper hole given on the board. If it is not, you have put it in reverse. Okay, that is a problem. Your board will not work. Only solution for that is you remove the IC and turn it and put it back in. Now the problem in doing that is, when you are soldering, you are actually heating the component. Okay, you are heating the component, and components have a limit of how much stress, thermal stress they can take, how many times you can reheat them. Okay, so if you are doing this multiple times, taking out, putting it back again, when you are taking out, you have to first, to put in you have heated, then to remove you have to again heat. Okay, then to remove the additional solder what is there on the pins, you have to heat it, then you put it in again, you have to heat. So you have to heat, cold, cool it, heat it again, multiple times you are doing this, which may cause the component to go bad. Okay, so that has to be avoided, but still this is a necessary step. You need to know if the components are mounted properly or not. Okay, then in this board we don't have any surface mount components. There are something this is a surface mount board with no components. Okay, here wrong alignment is, if I mount a component here, it is not making proper contact with both the pads. Okay, one pad it is making connection, other pad it is not making a contact. Okay, so if you look carefully, you will be able to find this out, but sometimes even with visual inspection we will not be able to find this out. So the first step is to ensure whether all parts are placed properly and they are aligned properly. So this is the step what we need to take. So the second one, all socketed ICs alignment orientation is fine or not, all leads are properly soldered or not. Okay, so that is another one. Are there any solder bridges? When we say solder bridges, it is like when I solder on this board, okay, two close lying pins, they should have not been connected, but when I solder, because I gave more soldering solder here, they made a contact and it caused a short in the board. Okay, it caused a short on the board, which is bad again. Okay, so now your board, you are creating a defect there. Okay, so you are creating a defect, so we have to be careful. So we have to check for such errors. Okay, then residual solder flux. Now to solder, you use a flux solution which enhances connectivity as well as sort of cleans the surface. Two purposes. Now if you put too much of flux, basically it does not melt properly and it can form a region within the solder, which will be, soldering flux is a insulating material. So what happens now, the contact is not properly defined. Okay, so contact does not get defined properly, which may lead to failures. Okay, then the next one, whether all the components are seated properly, and once you finish all these steps, next what you do is you again measure the resistance between VCC and ground. Okay, you measure the resistance between VCC and ground. Bare board, you got it as infinity. Now once you place all the components, it will be a finite value resistance. Okay, it will be a finite value resistance, and that resistance value depends on how much load is there on that VCC pin as well as ground. Okay, so depending on that you will see different resistance. Now if you see that resistance to be very low, okay, very low, almost close to 0, that means there is a short in the board. Then you cannot use the board, you have to find out where the short is. Okay, so this is what is required, right? So once you do all this, now you ascertain everything is fine here. The next stage is powering up of the board. Okay, now when you power up the board, in this case I have to give 5 volts and ground. So I turn on the power. Okay, I turn on the power. Now when I turn on the power, I should not give a possibility where this can take very high amount of current. So in your power supplies there is always an option to limit the current. Okay, there is an option to limit the current. So we have to set the current limiter on, okay, and then power this up. Okay, now what does that do is, if this board draws additional current compared to whatever you have calculated this board should draw, okay, if it goes above the set limit, the output voltage is turned off automatically by the supply, okay, thereby safeguarding your board. Okay, and there is an indication there, see, indicating that it has gone to short circuit mode or constant current mode. Okay, so then you can find out that this is taking more current than what it's supposed to. So then you know there is a fault. Okay, so this is what you have to do. Now assume it didn't take, but now after a while you keep it running for say 5 or 10 minutes. You have to also have a sharp nose. Okay, if there is any smell indicating there is some burning happening, that is a clear indication there is some problem in the board. Usual cause is you are supposed to take power from these pins. Okay, and this is the supply input where you are going to take large amount of current. Then individual components take current in moderate amount. So now assume that instead of giving a plane for carrying this current, large current, you have just given traces. Okay, small thin traces. So thin wires have higher resistance, right? Thin wires have higher resistance, and when more current flows to it, the wire starts heating up. So first thing, if it is an external wire, the insulation will start melting, so you can smell it. Okay, inside the board, because it is a FR4 material, the track is inside, track still heats up, so the top layer starts getting corroded, okay, charred. Okay, it gets starred. And if it is a very thin trace, the trace itself might break over continuous use, because it starts behaving now like a fuse wire. Okay, so it will break first. Okay, so we have to be careful. So we have to keep the board on for some time and see whether it is working properly. Both temperature also will increase, board temperature will also increase, as well as if there is any fault you will also get the smell. Okay, so both these should be checked. And if nothing happens, maybe 10 to 15 minutes you keep it, finally everything is fine, you then measure the voltage. Okay, you know, assume for this board the voltage should be 5 volts, and now I use a regulator here to generate some intermediate voltages. I measure all those voltages, see that it is as per the design specification. So if this much is done, your first job is done, okay, as a hardware engineer. So you have completely tested this board. Now once this much is done, next stage, if it is embedded, for example this is a microcontroller board, to continue further testing I need the help of software team, where they can write a small piece of code to light this LED. Okay, so then I can check the trace from this point to this LED is working fine or not. Okay, I run a small piece of code which will blink the LED. Okay, then I know this works, connection also is working fine. Okay, so this is the process. So after this, next process we always require help from some other teams. Okay, so is this clear, the different steps? Right. Okay, so now these are set of 9 rules which can be used for any fault detection or any bug detection or anything. Okay, these are generic rules, so it is not that it is only for hardware or for software, nothing like that, it works for any of this. Okay, the first rule is understand the system. So if I am testing something, first I need to know how the system is supposed to work. Okay, if I don't know that, then I will not be able to test. Okay, this you guys would have already understood by now. You go to the lab, you do an experiment. If you don't know what that experiment, what to expect as output from that experiment, whatever you get, you have to believe that. Okay, then basically when you show the results to the faculty, he will say this is wrong, repeat the experiment. Okay, there we went and did our experiment without any understanding of the circuit. Okay, so the first thing, whenever we are testing, we should know how the circuit is supposed to work. Okay, it is not that I need to know each and every point, maybe not necessary, but at least what is expected when I give a particular input, that much I need to know. Okay, so this is what is expected. Okay, if you know more than that, how the system is designed and what all components are used and how they tend to work, it actually improves your testing skill. Okay, testing skill. Okay, so this is the first step. So you need to, if I ask you to test something, first thing you need to ask me back, give me details of the product which I have to test. What is its design specification? What is its how you have designed? What are the different components used in design? Where are the data sheets? So you require a lot of reading ideally to test a product properly. Okay, so this is what is required. The second one, we should be able to make it fail. Okay, if we can't make it fail, we can't test it. The reason for that is, any of our hardware, okay, you design 100 systems, okay, 100 systems of this. Okay, take this example, this is a Asus phone. Okay, they might have manufactured 10,000 pieces of this, 10,000 pieces of this minimum. Okay, 10,000 pieces, each 10,000 is unique. Okay, they will be unique, they will not behave exactly the same way. All they do is they work in a particular range. Okay, within that range they will match. Okay, but they will not behave exactly the same way. Okay, so this is what we have. That is because the components used inside, each of them have their own tolerances, and whatever component used in one may not be the having the same value as what is used in the other. There will be a small deviation. Okay, and because of that, each devices or each product's functionality will be small, having a small deviation. Okay, that is okay, that is accepted. Okay, now when a customer comes back and says my phone doesn't work, okay, my phone doesn't work, I pressed the power button, the power off, on or reset menu did not pop up. Okay, so this is a complaint. So now to really test this condition, first thing is you have a test board with you on which you are testing. Customer is somewhere else, so you need to be able to reproduce the same failure on your test board. Then only you can debug why that happened. Okay, why that happened. And the board what you have may not be the same board as what the customer is telling that the complaint is. So unless you make this fail, okay, you can't really debug it. Okay, first thing, by making it fail, what you are ascertaining is there is actually a fault like that, because sometimes it can so happen simply there was a wrong connection on the customer part. Okay, and he is claiming it to be a failure, which is not actually true. Okay, which is not actually true, but you can't simply say it on his face, no, what you are doing is wrong. So we have to still test it and come back with a proper solution. Okay, so we have to first make it fail. So making it fail ensures two things: really that fault exists, and what are the reasons or what are the conditions which create that fault. So both things we can ascertain. Okay, so this is what we say. The next one is quit thinking and look. Okay, what this step means is, I can sit here for days together and think of possibilities which create that fault. Okay, so I can keep on thinking, but if I keep on doing this, basically I will only be in my seat thinking only. So we have to stop sometime, think this many possibilities I will test first and then do. The steps look trivial, okay, but it actually are what is followed when we try to debug. Okay, so we have to stop thinking at some time and start doing, start checking the devices, start checking the voltages, start probing. We have to go and try to work in the lab. Okay, the fourth one, divide and conquer. Okay, divide and conquer. What this means is, again coming back to the phone example, this phone has too many components. Okay, too many different blocks, too many different components. If I try to pinpoint a fault, I mean taking look everywhere, it is not going to happen. Okay, so I need to first divide this into blocks. Okay, which block may have the problem. Okay, find out. So I have to divide part by part, make it into smaller chunks, and finally identify which location the fault is. Okay, so this is what is meant by divide and conquer. Okay, the next one, change one thing at a time. Okay, so change one thing at a time is, I found some resistor was not mounted properly. Okay, some resistor, say 3 resistors were not mounted properly in the defective board what I got. Okay, so now I know there is a defect and I found that 3 resistors are not properly connected or the values were slightly different. What I need to do is, I need to individually change one resistor, check whether that fault exists. Okay, now one thing I can do to save time, all 3 I replace. Okay, all 3 I replace together and see, it works fine. Now board works fine, but I don't know the reason which caused that fault, whether it was one of the resistors or all the 3 resistors. Okay, so whenever I am changing something in a system, I have to change one thing at a time and check. Okay, so this is what is required. Okay, then 6th point, keep the audit trail. Okay, when they say keep the audit trail, whatever I am doing, I need to document that. Okay, otherwise what is going to happen, if it is a huge task of testing, you may be doing repeated things again and again, wasting time. So you need to keep track of what you have done, what are the steps. Now it is not like tested for this, no, exact procedure. Okay, this is the input given, this is the output expected, this is what I got, I made this change, I got this output. Okay, so you have to have complete information on what you have done. Okay, 7th one, check the plug. Okay, the step is given as check the plug, that is to mean first check the obvious things. Okay, so one common mistake which even in our normal lab it happens, we connect the circuit, don't turn on the supply and we are checking the output. Output is not coming, we do everything, then check the supply. Okay, that is why the name check the plug. First thing, most obvious ones you check that. Okay, so this is what we need to do. Get a fresh view. Okay, so what it says is ask for help. 3 hours in the lab not working, you simply sit, nothing is going to happen. Okay, so you have to ask for help. So ask with your friends, because they will provide a better perspective or a fresh perspective. Okay, so they may be able to debug this. Then if you didn't fix, it isn't fixed. Okay, unless you ascertain that you have fixed it, it is not fixed. Okay, it can so happen that output was not coming, you turned around to call the faculty, and as you turn back again it is coming. Okay, output is coming, that can happen, or the reverse can also happen. Okay, now you didn't fix it, it automatically fixed by itself, so you don't know now what was the issue, what was the correction. Okay, so that is what is meant. Now one possible reason, some wire was loose, when you turned around your hand touched that wire and it made a proper contact and you are getting the output. But I know it because from my experience, you guys don't know it because you are doing it for the first time. Okay, so this is the case. So unless you yourself don't fix it, you have to assume that it is not fixed. So these are the 9 steps for any testing or any debug, you have to follow this. Okay, the thing is, all 9 we may not follow in the same testing. Okay, some of them we take, some of them we don't. Okay, so for example, if it is a single small 1 IC circuit, we may not be doing divide and conquer. Okay, if it is a huge project, divide and conquer. Okay, so in monostable circuit, divide and conquer, all you can do is remove one resistor, that is it, because it is only having some 5 or 6 components there. Okay, so some steps you do, some steps you don't know, but these basically are all the different steps what you can have when you are trying to debug a circuit. Is this fine? Clear? Right. Okay. Now, okay, so let us take one example to see whether we can debug. Okay, do you guys remember this circuit? What circuit is that? It's a bridge rectifier. Okay, so this is a bridge rectifier. Okay, and with a resistive load. Okay, so the supply voltage is basically coming from AC mains through a transformer. Okay, so that is what is given to the bridge circuit. So the rectifier is a circuit which will convert AC to pulsating DC. Okay, that is the job of a rectifier. So what am I expecting here? I expect sinusoidal positive half cycles to be present. This is what I expect. Okay, so I have 4 diodes. Okay, so this is what I am expecting. Okay, okay. So you guys remember what the full wave rectifier output is supposed to be? Okay, now the specifications are given here. So this circuit was designed, somebody designed this circuit and it got fabricated, and now the customer complained that the waveform what he gets is this. Okay, the design was full wave rectifier. Okay, the waveform is of a half wave rectifier. Now what could be the issue here? Diodes are reversed. Now why do you know that diodes are reversed? First thing here, required knowledge is you knew how the system is supposed to work, right? So understand your system, you already have the understanding of the system. Okay, now we may not apply these steps whatever we discussed as is, but we by default we do that. Now if you didn't know how a full wave rectifier is supposed to work, you will not be in a position to detect this, isn't it, right? So since we know we are supposed to get 2 pulses, but here we are not getting the 2 pulses, so I know there is a fault. So it is behaving like a half wave rectifier. So diodes are not working. Which diode is not working? Which diode is not working? Now this is a simulated waveform. Okay, this is a simulated waveform here. So this is where the sinusoidal wave starts. Okay, and this is how he proceeds. Okay, so I am getting output only during the positive half cycle. So for to ascertain how the output behavior is, I need to probe both the input voltage as well as the output voltage. So when I do that, I will know that positive half cycle is present, negative half cycle is not present. Now if I know that, what information will I get? Yeah, which diodes? So there are 4 diodes here. So the fault is either in D3 or D4. Why? During the positive half cycle, D1, R1, D2, this is the path. During the negative half cycle, the path is D3, R1, D4. So now since the negative half cycle is not coming, the fault would be either in D3 or D4. Okay, so now either one of them can be faulty. So now what would be my next step? Remove one D3. Okay, check for its whether it is working fine or not. If it is working fine, check whether it was properly connected. Now the problem can happen if I had reversed the diode also, the same problem comes. Okay, instead of connecting this diode in this fashion, if I had reversed this, the behavior of the circuit would be exactly similar to what you have seen. Either the diode is faulty or the diode is connected in reverse. So you have multiple solutions now. What could be the fault? You need to now check for one condition at a time. Check whether the diode is mounted properly. Anode and cathode are proper. If it is proper, check whether it is diode is working fine or not. Okay. So how do you check the diode? Use the multimeter in diode testing mode and connect it across anode cathode. As you connect, he should show a VF drop across it. If you reverse it, he should show open circuit. Okay. So you check that. So then you identify this is the case. Okay. So this is how we proceed. Is these steps clear? See, we are applying the same steps, not actually as a rule. Here and there we are doing the same. Okay. So I should know the system. I should know how the system works. If it is fine, then I can ascertain what is the fault. Then I can find out where is the fault. Okay, where is the fault, and finally I am able to now rectify and I give back the board. Is this clear? Right. Right. So now same board, you have rectified the fault. Now the customer says I want a clean DC, so add a capacitive filter. You have added the capacitive filter and you are now giving him the product. Okay. Now with that capacitive filter, what sort of output are you expecting? Reduced ripples. Okay, you expect reduced ripples, so you will get a it will start from 0, go to some peak value, then slightly decrease, keep on increasing. So there will be a small amount of ripple. This is what is expected. Okay, but he comes back and says, I am getting this output. What could be the reason? Capacitor value not proper. If the capacitor value is not proper, you will not get this waveform. This is a full wave rectifier output, isn't it? Without the capacitive filter. So basically it is like capacitor is not there in the circuit. The behavior is like capacitor is not there in the circuit. Okay. Now when you put the capacitor, actually you are putting the capacitor in shunt with your output, connected between the VCC and ground. Two faults can happen in the capacitor. It can be open circuited or it can be short circuited. If it is short circuited, what is going to happen? Your output would be 0. Okay, your output would be 0. Now here output is non-zero. Okay, the output is non-zero. Okay, that means capacitor is not shorted. Okay, but the capacitor is not having any effect. Okay, so one probable thing is capacitor is not properly connected. So one lead of the capacitor might be floating. Okay, so it is not made proper contact. Okay, so this is how we ascertain. Okay, so we needed to know how the system works, what happens when the capacitor is shorted, what happens when the capacitor is open. Okay, then we could find out the problem, find out the defect in the circuit. Okay, so this is how we follow. And additional steps what we need to do is we have to now note down all this to say now if the capacitor is not mounted, then you will get this sort of a waveform. Now why that is helpful? Now somebody else is now checking the circuit. By looking at the waveform, he can tell, okay, this problem is because of the capacitor. Okay, so the next person again need not spend time on trying to debug the same issue. Okay, so this is what happens. Okay, so normally when you go to a company, software or hardware, for every bug there is a tracking system. First they will open the bug, give all the criteria, what caused the bug, what condition the bug has happened, and what is the behavior of that. Okay, then when you try to solve it, you always have to update that content there, like what you have done and what was the behavior, whether that rectified the bug or not. Okay, and only once you have ascertained that whatever you have done completely removes that bug, you can close that file saying that bug is now removed. Okay, so that is how the procedure is. So you have a bug tracking system there. Okay, and generally if it is a software or a hardware team, they always say how well you do by looking at how many bugs are opened, found, and how many bugs are eliminated. Okay, within a week. That shows your performance. Okay, that shows how fast you are opening and closing a bug. Okay, opening more and more bugs is good for the testing team. Closing more and more bugs is good for the design team. Okay, so this is what it is. And finally, if you can debug your circuit well, you can design the circuit better. Okay, because all these knowledge of debugging a circuit will make you a better designer. Okay, it will make you a better designer. Is this clear? I hope you understood what all goes into testing. Right. So now all this is fine. Now we go back to the same point, quit thinking and look. Okay, so we will stop talking and we will try to demonstrate one circuit, okay, which you guys know. Okay, so this is a monostable multivibrator. Okay, monostable multivibrator. The requirement for this circuit is, if I press that switch, okay, if this switch is pressed, okay, I have a motor which should run for around 5 seconds. The motor should turn on, stay on for 5 seconds, and then turn off automatically. So this is a requirement. So the customer specification is, when I press the switch, my motor should turn on and it should run for 5 seconds. Okay, so this is a requirement. So what design I have done, I have taken a monostable multivibrator, which we know once when we trigger, he will generate a pulse. Okay, and I can fix the pulse width. Okay, so I know that it should run for 5 seconds. So I use appropriate resistor and capacitor. The values are here, 560K and 10 microfarad. Okay, so this gives me around 5.6 seconds, okay, of pulse width. Okay, that is got using this particular formula. Okay, and this one I am connecting it to a base of a transistor because the motor current requirement is higher. Okay, the motor requires around 30 milliampere of current, which is not supported by 555 timer. Okay, he gives a low value of current. Okay, so to increase the current drive, I am connecting this transistor. So when the pulse is high here, the output of the 555 is high, transistor is on. So if the transistor is on, current flows through the motor. So motor turns, supposed to turn. Okay, so the motor is supposed to turn. Okay, and then when this pulse goes off, the motor is supposed to turn off. Okay, so next once again when I press the switch, the same thing should happen. So every time I press the switch, motor should turn on, stay on for 5 seconds, it should go off. This is the requirement. So we will try to make this circuit here, connect this circuit on a breadboard, see if it works properly or not, and see what could be some issues if we have. Okay, so the problem is we will not learn debugging if every time when we connect the circuit, if it starts working, then our debugging skills will be poor. Okay, because we don't test. Okay, it works, so we don't test. Okay, so we will try to make the circuit not work and try to debug. Okay, so that is what we will try to do here. Okay, so hopefully it will not work on the first case, so that we can debug, right? So this is okay. So I would like you guys to note down this, because when we are doing the circuit, this will not be there. So it's a monostable